Hey geometry friends, here we are in chapter 7 looking at section 7.4. We're going to talk about parallel lines and proportional parts. Today we'll discuss the mid-segment of a triangle, and basically the mid-segment we could read here, this is directly from your text. The mid-segment is a segment that connects the midpoint of two sides of a triangle. So a triangle will have three mid-segments, as we see here, because RQ connects the midpoint of AC and CB, and PQ connects the midpoint of BC and AB, and you can see RP does the same thing for these two sides. So what we get is this triangle inside that is created by three mid-segments of this triangle. So Theorem 7.4 gives us the triangle proportionality theorem, and it basically says that if a line is parallel to one side of a triangle, so here that line would be BE, if we've got a line parallel to one side of a triangle and it intersects the other two sides, then it divides the sides into segments of proportional lengths. So this segment, because it cuts two sides of the triangle, will now, and it's parallel, it's going to make this AE to ED the same ratio as AB to BC, as we see here. So here in example 1, we're going to use that theorem we just discussed. Here we have triangle PQR, and we see that ST is parallel to RQ. And we're given the fact that PT is equal to 7.5, TQ is equal to 3, and SR is equal to 2.5. We are to find PS. One of the most important things to do is to honestly just write down the information given. So I'll put my 7.5 here, my 3 here, my 2.5 here, and then PS, I'll put an X. The theorem told us that the sides are now cut into proportional pieces, therefore this is to this, PS is to SR, or X is to 2.5, as PT is to TQ, or 7.5 is to 3. We'd solve this by cross multiplying. When you multiply these guys together, we get 18.75, and multiply these guys together, we get 3x. And to solve for x, or PS in this case, we're going to divide both sides by 3. When I do that, 3 goes into 18 6 times, and 3 goes into 75 25 times. So I get 6.25 is the value of PS. Theorem 7.6, the converse of the triangle proportionality theorem, tells us that if we have a line that intersects two sides of a triangle and it separates the sides into proportional corresponding segments, then we know that that line is parallel to the third side. So given this information that let's say EB is to AE as DB is to CD, then we can conclude that these sides are parallel. Here in example 2, we're going to determine if lines are parallel. So we're given this triangle DEF, and we're given that EH is 3, HF is 9, and DG is 1/3 the length of GF. So that's going to make us decide or have to write this in a way that'll make it convenient for us. So if DG is 1/3 of GF, then if I call DG, let's say X, GF would have to be 3X because DG is 1/3 of GF. I hope that makes sense. So what they're asking us here is DE and GH parallel. And hopefully you can see that this ratio is similar, but let's check it out. If I have 3 over 9, is that the same as x over 3x? And if I reduce this guy, I get 1/3. And if I reduce this guy, I get 1/3 as well. And so that checks out. These guys are proportional. And indeed, yes, DE and GH are parallel. Theorem 7.7 gives us the triangle midsegment theorem. A midsegment of a triangle is parallel to one side of the triangle and its length is 1/2 the length of the side. So remember earlier we talked about the midsegment. If you've got a midsegment, it will definitely be parallel to the other side, to the side it's not intersecting, and the length of the midsegment will be half the length of the segment it is parallel to. So here, in example 3, in the figure, XY and XY and XZ are midsegments, these guys, and of the triangle RST, find the measure. So if we know that XZ, that's what we're looking for now, is a midsegment, the side it's parallel to would be RT, and also it will be half of RT because of the last theorem we just talked about. So XZ must equal 6.5 because that's 1/2 RT, which is 13. Let's check out ST. ST is this segment here. It is one side of the triangle. If you notice, we can look at this segment here, XY. That's the midsegment. It's parallel to ST, and it's also half the length of ST. So ST has to be twice. This is all from the theorem we just talked about. ST has to be twice XY. And since XY happens to be 7, we know that ST is 14. Finally, let's look at this angle here, RYX. When I come to the picture and I take a look at RYX, let's see if I can find it. We're talking about this angle right here. So RYX. When I look at RYX, I recognize that it is created by this side and this line here. When I look at this side and this line, I can't help but think about parallel lines cut by a transversal. So here, I'm going to highlight this guy. We know that this is parallel to this. That's from the theorem we just talked about. The midsegment is always parallel to the third side. But then we have this transversal cutting through two parallel lines, and therefore these two angles must be congruent. They are alternate interior angles. And because I have that congruency, I know that angle RYX is equal to 124 degrees. We have a pretty cool corollary that comes from the theorems we just talked about, proportional parts of parallel lines. So if you take some parallel lines, if 3 or more parallel lines are intersected by two transversals, boom, boom, then they cut the transversals proportionally. It's kind of like, almost like as if we had a triangle here, and remember how the sides are cut proportionally? Well, we don't even need a triangle. What we really need is to have lines that are parallel. So if you've got 3 or more lines that are parallel and you've got two transversals that are cutting them, those transversals will be cut proportionally. So specifically, we see that AB is to BC as EF is to FG. Hopefully you see that and that makes sense. Kind of cool. We also have this guy, this corollary, which gives us congruent parts of parallel lines. So if you've got 3 or more parallel lines cut off, all right, let's try it again. If three or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. So you can see the picture here. You've got these parallel lines, and it happens to cut this transversal into congruent segments. Then what I know is that this transversal also will be cut into congruent segments. And this one that's not even drawn is cut into congruent segments. You guys get where I'm coming from? Any transversal that cuts through these parallel lines will be cut into congruent segments because it happened to one of them. Is that all right? So with all that knowledge, let's go ahead and apply it to our last example. So here we've got, we're going to look for X. Let's use a pen. We'll look for X and Y. And we see that we've got these parallel lines, and they're cutting this transversal into equal parts as denoted by these hatch marks. Therefore, this is equal as well. So I have the equation 3y plus 8 is equal to 5y minus 7 because these guys have to be equal. And similarly, jk and kl are equal. 6x minus 5 is equal to 4x plus 3. And solving this is just the same old stuff that we've been doing. We are totally building our algebra muscles every time we solve an equation like this. So we're doing our thing. Move the 7 to the other side, you get 15. So 2y is equal to 15 implies that y is equal to 7.5. On this side, we subtract 4x from both sides to get 2x minus 5, which is equal to 3. We're going to subtract 8 from, we're going to add 5 to both sides to get 8 on this side, divide both sides by 2, and finally we get that x is equal to 4. So y is equal to 7.5 and x is equal to 4. So here we are with the final discussion, not really an example. I'd like you to try this. You should use your compass to try to figure out how to trisect a segment. So you start off by drawing a segment here, some segment AB, and then you draw an additional segment from A or ray of whatever length. And then you take your compass and you mark off 3 equivalent spaces. Well, how you do that is you put your point here and your pencil line here. Then you put your point here and you carve out a pencil line here. Then you put your point here and you carve out another pencil line. So you get something that looks more like this. And then you can draw lines like that. And then you know that the intersection point of these lines would have to be equidistant and therefore equal in terms of having trisected that segment, which is kind of cool. I like to see you guys get that done and show it to me on Friday. Other than that, let me know if you have any questions, and I look forward to seeing you soon. Take care.